Lecture 16. In Lecture 16, we're talking about the robust tracking problem. What exactly is the robust tracking problem? So here's our list of topics we've been talking about. We're talking about the robust tracking problem here. And basically, in general, we wish to track a continuous time signal given by a Laplace transform like this. And in general, it's not a step input. In the previous approach, although we theoretically could control the system to track such a signal, it turns out you don't actually get ripple free. And so the important question is, why wouldn't you get ripple free? So in terms of robust tracking, it turns out that we have a system that looks like this. And in our case, so in general, we may have a time delay and so forth. We have an actual transfer function. In tracking a step input, this signal in steady state will be a constant, okay, which is easily put out by a D to A converter. Constant output, D to A converters can handle that. But so for step input, you get ripple-free tracking because the kind of signal this needs to be in steady state, it can be. All right. So let's look at an example. So here we have this system, okay, and we desire to track a sinusoid. So here's the sinusoid in continuous time. Here it is in discrete time. Okay, so this is an unstable system. We're going to try to control it. So our minimum order solutions of our Diophantine equations, these are the things that we get. When we do simulation, this is what we get. So notice that I get like a response that is not smooth. It's kind of rough. So this is R and Y. R is the yellowish, Y is the output of the system. So you can see they overlap, but they're not perfect. It's not smooth. The output of the system is not smooth. And if you actually take the difference between these two signals, this is the signal you get. And you see that the error, it does not, so notice in discrete time, the error values are 0, but in between samples, we have non-zero response. And that's because, again, the controller can only put out piecewise constant signals. It can't put out a smooth sinusoid, and so we get these kinds of things. So we get what is called steady state ripple. Okay, so it's like, well, how do we get ripple? I thought we had a ripple-free deadbeat controller. Well, it's deadbeat in the sense that it goes to 0, the error goes to 0 in a finite number of steps, but it turns out that in between samples, it can't go to 0. So that's a significant thing. So basically what happens is this. So if this is a sinusoid, and this is a sinusoid, so that you get perfect tracking, then it turns out this signal must be a sinusoid. However, it is piecewise constant. It cannot be a sinusoid. So there's trouble in paradise because of the fact that we cannot have a continuous time signal here. A smooth signal here, like a sinusoid. We have a piecewise constant signal, stair-stepped. And so, in fact, the whole notion of a frequency response says this. If I apply a sinusoid of a given frequency, the output in steady state is going to be a sinusoid of the same frequency, different magnitude, different phase. The magnitude of the output is going to be equal to the magnitude of the transfer function evaluated at that frequency, and the phase is the phase of the transfer function evaluated at that frequency. So there's a relationship. So to get a sinusoid here, when we apply a sinusoid to a system, we get a sinusoid out, different magnitude and different phase. So if we want the output to be a sinusoid like this, that is with a fixed constant magnitude of 1 in this case, and no phase, then the input to the system, U of t, needs to be, we basically have to apply the inversion principle. So this needs to be the inverse in order to get this. So notice here we had plus phase, we had to subtract the phase. Magnitude is m, so we divide by m. Okay, and so if we apply this sinusoid to the input of our system, we will get this sinusoid out. So in in steady state, this needs to be the input if this is going to be the output. Okay, so again, in steady state, I have a controller. So here's my controller, 2 degree of freedom controller, 2 inputs, 1 output. Somehow this controller has to generate this kind of a signal in order to get this output to match this input. How can that even happen? So we rely on an important principle from control systems called the internal model principle. The internal model principle says that for asymptotic tracking of the reference signal, the forward path must contain a model of the reference signal. Okay, so that's the concept of a model. So what are we talking about when we talk about a model of the reference signal? Right, so here's our reference signal. We have the Laplace transform of it. We now have what's called a tracking model, which has some numerator and denominator, nm and dm. And in order for the system to track this kind of signal, which may be a sinusoid or some other signal, the denominator of this needs to be equal to the denominator of this, of the reference. Okay, so I need that. Okay, so now I have this model. I haven't selected the numerator yet. We'll come back to that and figure out what we can do with that. But for now, the denominator is the same. Okay, so how do we incorporate this tracking model into our control scheme? Well, this is how we do it. We put m of s in series with our plant. And now we call all of this our plant. Our plant has a new input now, v, that goes into this model. And so you can think of this model as being a kind of filter. Okay, it's a kind of filter that smooths out the signal from this to give a signal here that's smooth. Okay, instead of stair-stepped. Okay, so that's what's actually happening. But it's not just any filter, it's a particular filter. It's a filter that is matched with the reference signal. Okay, so we can look at it this way. And now we lump this together as our plant, and we design our 2 degree of freedom controller. Okay, so in the blue here is actually our controller, and our controller includes that model. Okay, so again, incorporating the model, we have the reference signal, we have the model, and so that's what we're going to work with here. So now when we take the C2D of the system, we actually have to incorporate both m of s and p of s. Let's look at an example. So here's this system that I tried before. The reference signal is a sinusoid. Here's the Laplace transform of that. I'm going to choose this model. So notice I don't necessarily choose the numerators to be equal to each other. When I take the H transform, I'm going to include m with p. Okay, I'm going to include m with p, and so I get all of this stuff. I solve my Diophantine equations. And when I simulate now, notice I get a nice smooth response. Here is the control signal. Notice that it becomes a sinusoid. V of t is the input to our model, m of s. And you can see that this goes to 0. It should go to 0. Okay, it should go to 0. And so basically what's happening now is we have set up our model, m of s, to become an oscillator at the right frequency and giving the right magnitude and phase in order for the output of the system to be what it needs to be. Okay, so but in particular, we can see that the control signal now is in fact a sinusoid, the kind of sinusoid it needs to be. So V of t is this signal, okay, and so we can see that it goes to 0, and then the u of t is the actual input to our plant. So now what model do we choose? Well, we've already chosen the denominator for the model, but what do we do for the numerator? Okay, so that's the important question. Well, we have some options. Here are some options. We could choose a constant as the numerator, or we could choose the numerator to cancel stable plant poles. Okay, remember, we cannot cancel unstable poles, but we can cancel stable poles. So these are two options. Any other options will likely degrade the response. So what if we choose a constant numerator? Well, a constant numerator generally will add delay to the forward path, which makes the control problem harder. However, it does add smoothing, which is a nice thing. So there's pros and cons to using a constant numerator. Using a constant or using a cancellation of stable poles in general will remove delay from the forward path, generally making the control problem easier, but you may have the problem of inexact cancellations. And so the question is, how robust is it if you don't get exact cancellations? So these are some important questions. Well, let's look at an example to see how all of this works. So I have this unstable plant, so it has a pole in the right half plane in the continuous time, and then I have two stable poles. I'm going to track this reference signal, so it's a sinusoid of frequency 2. Here's the Laplace transform of that. And so I have several different models available to me. So this one has a constant numerator. So notice the denominator is the same in each case. And I need to choose m to be causal, which means I can have at most as many zeros as I have poles. Finite zeros. So in this case, I'm going to cancel this pole. Here I'm canceling 2 poles. I use a large gain, and so these are what I get when I add. So these are stable poles from the plant, and I'm canceling them. Okay, so these are the 3 models I'm going to consider. So now I want to evaluate how each of these models performs in terms of the overall control problem. Okay, so I've got some models. So now when I multiply them by the plant, notice in this case, I have added these 2 poles, so now I have this plant now has 4 poles and no zeros. Notice in this case, I've actually canceled one of the poles. Here I've canceled 2 of the poles. Okay, so here the model is more complicated, but the system is simpler. Here the model is simpler, but the overall combination is more complicated. So I go through and I find the minimum order controller in each of the cases for model A, model B, and model C. And I simulate. And here are the results that I get when I simulate. So I have the 4 different options. The green is the actual sinusoid I'm trying to track, and then I have these 3 different responses. So notice that so each of the responses is a little bit different, but they eventually lock on to the sinusoid and they stick with it. Okay, so this is the error, the difference between the output and the input, and you can see the responses in each of these cases. So the case when we cancel no zeros is this case. The case when we cancel 1 pole is this case, and the case when we cancel 2 poles is this case. And so you can see the more cancellations, the faster settling, and also the smaller error magnitude. Okay, so the magnitude of the error is smaller in these cases. So in this case, canceling actually helped us in terms of the control problem. So we can slow the process down, add some robustness, and so this is what we get. And so I've done a little optimization, and so you can see what we get here. So notice that the over here, the error went as high as 0.9. Here the error is a little bit larger, but again we allowed a longer delay. And here are the control magnitudes according to those different responses. So I have 3 different responses. I've added some robustness to the system. I have slowed the process down, and so this is what we get. Now, in this case, we've simulated the system with the actual plant being the nominal plant. Okay, what happens now if our actual plant is different than our nominal plant? Well, we're going to look at 3 different possibilities. 1, when the gain of the numerator is changed. 1, where we change the unstable pole value. And 2, where we add an extra pole to the system. Okay, so in this case, we've changed the gain value. The gain value in the nominal case was 30. Here we have 20. and you can see the responses of the system. So notice that this red guy is the response when we don't cancel any poles of the system. And you can see it steadily is getting worse. It's actually an unstable response that we get. Okay, so notice we're not designing with this in mind. We're designing with the original transfer function in mind, but the actual transfer function is something different. So you can see that in the case of no cancellations, you actually get an unstable response. In the case that we cancel one pole, we see that a response is not converging, but at least it doesn't go very far away from the actual response. In the case where we cancel two poles, we see we actually get convergence of the response onto the actual sinusoid. So we can see, at least for this example, when we have that as our actual, that canceling two poles is actually more robust. Okay, now we have the proper gain. In this example, we have the proper gain, but our pole value, our unstable pole value, instead of being minus 0.1 is actually minus 1.2, and you can see the kinds of responses. Notice that, again, without cancellations, our system goes unstable. In this case, with one cancellation, our system also goes unstable. But with two cancellations, notice that we also, again, converge. The response converges and settles down to the sinusoid it's intended to be. So we can see again that by having these cancellations, we are more robust. So in this third example, we have all the right poles and zeros and gain, but we've added an extra pole. Okay, and these are the responses that we get. Again, without cancellations, we're getting something unstable. With one cancellation, we're also getting something unstable. It's blowing up. But with two cancellations, again, our system is stable and it converges just like it needs to be. So this gives us this helps us to analyze the responses of the system when we have various modeling uncertainty issues. So in general, the more cancellations, the more robust the system is. Or another way of looking at it is the simpler the continuous time system that you're designing the controller for, the more robust the system is. So this is the robust tracking problem. Here we've been trying to track a system, a signal that is not a constant. And so what we see is that we actually have to apply a model, a continuous time model in the loop in order to get the kind of signal that we need, that the system needs in order to provide the proper output. We've seen that depending on how you choose that model, the system may be more or less robust. So this is the robust tracking problem. Thanks for watching.